Another situation that occurs when we try to minimize logic is a situation where the output for a particular input code doesn't really matter. Okay, so we know that when we have a circuit, let's say for example, that has 4 inputs, and we'll call them A, B, C, and D, it has 2 to the n possible input codes. Okay, so it's got 0, 0, 0, 0, all the way up to 1, 1, 1, 1. And just by the virtue of having 4 inputs and having each input only take on the values of 0 and 1, we know that these 16 unique input codes could exist in an ideal system. But in real-world systems, sometimes the inputs have some logic behavior that are tied to each other, where maybe A can never be different from C under certain conditions. And what happens is that it will limit the amount of input codes that actually can occur in a system. So even though we might have all 16 possible input codes, we may never get them in a real system. So we can take advantage of that when creating a circuit by introducing this new thing called a don't care. So a don't care is where you really don't care if the output is a 0 and a 1 for that particular input code. And we give it the unique symbol X. So let's see how we can use that to our advantage. So I'm going to fill in this truth table. So let's just say we had a truth table that is 4 inputs. So we're going to have 0, 0, 0, 1, 1, 0, 1, 1, then 0, 1, 0, 1, 1, then 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, then divider 1, 0, 0, 0, 1, 0, 0, 1, 1, 1, or 1, 0, 1, 0, 1, 0, 1, 1, and then 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay, so we come along and we look at our real world system and we say, okay, well, for this first code, I want the output absolutely to be a 0. For this code, I want to absolutely be a 0, absolutely be a 0, absolutely be a 1. This one, though, it doesn't matter. And it doesn't matter for a variety of reasons. The most common one, like I said, was that maybe this code just never will happen the way that the physical system is built. So we don't really need to drive it to a 0 or a 1. So let's just leave it at the truth table level as what we call a don't care. So I'm actually going to put an X in the truth table. Same thing, I'll have an X there, a 0 and a 1 here. And then let's just say that these ones will never occur. So let's just say that this was the logic behavior for a particular 4-input system. And this is very common when you build the real system. There are unique codes that you care about, and there are some codes that just may never occur. So let's take advantage of a don't care for the codes that don't occur, and let's try to create the smallest circuit possible. So the theory of a don't care is this. We will treat it as a 0 or a 1 when we implement the circuit to get the smallest circuit. Now, when we create a circuit, we will absolutely drive this to a 0 or a 1, because there's no such thing as a half, there's no such thing as a half in binary. So we are going to absolutely assign a specific code to this, but what we're going to do is we're going to assign the code, either a 0 or a 1, to get the smallest circuit. So it's very easy when you come along and you do this in a K-map form. So let's take a look at a K-map. And let's come along here and we'll draw our 16 cells. And let's go here and we go A, B, C, D. And then we have our code 00, 01, 1110, and 0001, 1110. And I pop these babies in there. So I go 0001, and I go don't care, 01. And then I go don't care, 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 don't care. So that's what it looks like in a K-map. Now, what I can do is I can include those don't cares in a prime implicant circle in order to create the largest circle possible. Now, if I look at that, originally, if all these X's were 0s, I would circle these 2 1s. But since I have the ability to treat any of these the way that I want, it would be to my advantage if I treated these 2 cells as 1s. So that allows me to extend the circle around them. By doing that, what I have done is I have said these 2 cells will now be treated, or will now produce outputs of 1s, because I'm going to create a product term for this particular circle. And the product term is simply going to be A and B are excluded, because it covers a region where A and B are both a 0 and a 1, and it covers a region where C is a 1 and D is a 1. So the product term for this is simply Cn of a D. And so what we can do here is we can say, okay, that's the new product term for that, and the output is simply F is equal to Cn of a D. Now when I do that though, what it's going to do is it's going to produce these codes for these two inputs, or it's going to produce outputs for these two input codes of a 1 and a 1, and then for all these other ones, since I didn't produce a 1 for them, they're going to output a 0. So what happened was this. We ended up going back into the truth table, and the way that we implemented the actual circuitry, the true output of the circuit itself would be like this. It would have treated, what is this? It would have treated the input codes 1, 1, 1, 1, so this one right here, it would have treated it as a 1, and it would have treated this one as 1, 0, 1, 0, or 1, 0, 1, 1, which is this one right here. So this is going to be cells 11 and 15. So right here, these would have gone to a 1. All the other ones would have been zeros. But those aren't really assigned until I actually create the logic expression for the final circuit. So I use these don't cares to my advantage to allow me to create larger circles, which essentially says I'm going to create a term which is going to produce more outputs or it's going to produce an output for more input code conditions. Okay? So that's how you treat a don't care. Now don't cares can be equally used when circling zeros. And this was just a sum of products example, but you can certainly do that with product of sums by exploiting don't cares.